Okay, for this video, we'll be going through general properties of wave, success criteria D, which is recall and apply the relationship speed of wave equals to frequency times wavelength. So this one will be our V, this is F, and this is wavelength, to new situations or to solve related problems. So basically, you are going to apply what we have learned previously. Okay, so let's look at question D1. At a particular instance, a transverse wave of frequency 25 Hz. So for us, we try to map the values to the physical quantity. So in this case, it is F. It is traveling to the right. That means now I know the direction of the wave. And if you know the direction of the wave, so later you can actually draw the next wave. Okay, so as shown in the diagram below, at that instant, the displacement at point X is 0. So this is our X. It is 0 because it's at the rest position, but it doesn't mean that the speed of velocity is 0, right? It's in fact maximum. So they're asking what is the shortest time elapsed before the displacement at point Y becomes 0. So if we look at point Y, it is actually at the trough. Okay, if it's at the trough, that means it's the displacement is maximum, although it's in the negative direction. Displacement is maximum and negative. So what is the shortest time taken before point Y, before this particle its displacement becomes 0? That means it will go up, right? So I think in my previous video, I talked about drawing the next wave and finding the direction. So for Y, we know certainly it's going to go up. Okay, and I also covered that in order to complete a complete wave, okay, the particle actually has to go through 4 steps. So before I solve the problem, maybe we go through what are the 4 steps. So if we look at Y, we started off at the trough. Okay, so maybe I just redraw here. Okay, so if this particle, if this is Y, okay, it actually has to go up. So this is our step 1. Okay, but it wouldn't stop at this rest position. Okay, because it has not complete one wave. Remember, we want the Y, particle Y, to actually go through a complete oscillation. So Y actually goes up to this rest position. It's going to go up again, right? So after 2 steps, it will actually end up at the crest. Okay, but it has still not complete one wave. It has not complete one oscillation. It must go back to its original. So after it hits the highest point, it will go down to the rest position. That is our step 3, and eventually it will end up at the same location. Okay, I hope you don't misunderstand my drawing, that it seems like Y has shifted to the right. Okay, it's not. It's just that I'm doing this so that you can see that Y actually goes up, up, down, down. Okay, so maybe if I choose another point here. Okay, so I'll just quickly say that if let's say this particle goes up, next moment it will come down, then will go down, then it goes up. So all of them will do these 4 steps to complete a complete oscillation. Similarly for pendulum, okay, so if I start from here, 1 step, 2 step, 3 step, 4 step, in order to do a complete oscillation. So if Y wants to go to 0 displacement position, it is actually taking 1 step. Okay, so we have the info of 25 Hz. So if I have 25 Hz, I can actually use this formula, T equals 1 over F, to get the period. So it's 0.04 seconds. Now within a period, there should be 4 steps. And therefore, 1 step would take 0.01 second. Okay, so what's the shortest time elapsed before the displacement at Y becomes 0? It's going to take 1 step, and we have calculated that 1 step is going to be 0.01, so answer is A. Okay, let's look at D2. Okay, so we have 2 kinds of graph. One is a DD graph, displacement distance. So very quickly, I can get the amplitude from the y-axis. I can get the wavelength from the x-axis. The other graph is for the same wave, but it's a displacement time graph. So I can get the amplitude from the y-axis, which is this, right? I can also get period from the x-axis. Okay, and if I have period, I can then get my f because it is 1 over t, right? And true enough, they are asking us to find the speed, which is v. So formula v equals f lambda. I can get lambda from my dd graph. I can get frequency from my dt graph if I know the period. Okay, so if I were to start from here, let us find a complete wave. So it's 2 cm. Okay, take note of the units. How long does it take to complete a complete wave, which is the finding the period, which is 0.04. So the period is 0.04 seconds. Okay, so you can either use v equals to lambda over t or v equals to f lambda. Okay, since I'm given a period, I found period, I will just use this 2 divided by 0.04, and answer will be 50 cm per second, right? Simple. So this is how you use your dd and dt graph. You find your wavelength, you find your period, you find your frequency, and together you can use it to find the speed. Okay, let's look at D3. Okay, diagram below shows the displacement position graph. Okay, so I can take it that this is distance. Okay, so maybe this is the start of the wave, where the disturbance happened. So this is 3 meters away from there. And of course, it's a transverse wave. And it's traveling from left to right. So if it's traveling from left to right, I know I can actually draw the next wave. Okay. And because this is a dd graph, I can actually find out the wavelength. Okay, just for practice, the wavelength should be 2 meters. Okay, but they are not asking for that. They are actually asking which of following graph depicts how the transverse wave will look like 1/4 of a period later. So a period is actually 4 steps. If 1/4 of a period, it is actually 1 step. Right? So this 4-step idea is very important. Okay, 1/4 of a period is actually 1 step. So we need to make every particle move 1 step. So let's take the crest because it's the simplest. Crest, you will take 1 step, it will be 1 at the rest position. Okay, so maybe I use a cross. For the trough, it will be here. Right? Crest will be here. So it seems like if I just rely on these 3 points, I will actually get a flat line, but that is not true, right? But I can use this to eliminate, because I know that 1 step later, this particle will actually be here. So that means A is incorrect. This particle will actually be here. That means this is not correct, right? So A is out. Similarly for B, B is also out, right? If I were to use these 3 particles, the 2 crests and 1 trough to help me. Okay, so we are actually left with C and D. So let's use this point at the origin. After drawing the next wave, which is actually going from left to right, right? Going from left to right, yeah. We know that its next motion for this point is actually going down. It's actually going down. So we look at C and D. Which one is that? It's C, right? And remember, the crest is actually going down to be at the rest position after 1 step, after 1/4 of a period. So we have it here. Okay, how about this? We have drawn the next wave. right? Just draw a vertical line. For this particle, it's actually going to go up, right? Because it's going to cut the next wave over here. That means it's now going to be at the crest. That's why we have this. So if you would like to practice, you can actually map out every significant points, which is the one at the rest position, the crest and the trough, and you'll get the answer to be C. Okay, so some other variations. In this question, they ask for 1/4 of a period. 1/4 of a period. So I've seen some other questions is half a period and 3/4 of a period. Okay. Okay, we continue on. This is again pertaining to a certain type of question. As a wave travel within a medium with different depths. Okay, example water waves. The wave speed V, wavelength will change. What wouldn't change? The frequency will not change. So I came up with this SSSS. Okay, same frequency. Okay, the frequency can only be changed at the source of vibration. Okay, this is important. The frequency can only be changed at the source of vibration. So example, if you're playing an instrument, okay, so, and you are the one that's playing, you are the one that's causing the disturbance, okay, so you, the frequency of the sound, of the wave that you produce, the frequency can only be changed by you. Okay, so this is what it means. Same frequency. And let's look at the next S. Okay, so imagine we're using water wave. So if the depth goes from deeper to shallower, okay, I highlight this S. So if it's shallower, right, what happens? The wave will become slower. The wave becomes slower. The wavelength will be shorter. So this is my SSSS. Hope this will help. Let's see how we can apply. Okay. So D4, the diagram shows a water wave in a ripple tank. The wave has a speed of 12 meters per second at R. So this is V, right? Over here, it is 12 meters per second. Okay. The wave crosses a boundary PQ, where the distance between successive crests changes from 3 to 1.5. So you need to interpret this. Distance between successive crests, that means the wavelength goes from 3 cm to 1.5 cm. That means the wavelength becomes shorter. So let's use our SSSS. If it's shorter wavelength, that means the speed will be slower. Frequency will be the same, right? And what else? That means it will be shallower. So where's the shallower region? The shallower region will be here. Here is shallower. Okay, because we have a shorter wavelength, which is 1.5. So over here is 3 cm. Now, what's the velocity of the wave at point S? So they are asking for here. Okay, so at R, it is 12 meters per second. What is the velocity at S? Okay, so let's use the formula V equals F lambda. In physics, it's very common to use this method. What is the thing that is common between these two cases? Now we have two cases, right? One is deep, one is shallow. So what is the thing that's common between both? Is the frequency. Right, because the frequency would not change. Frequency can only be changed at the source. Okay, change at the source. But because the depth of the water changes from deeper to shallower, so there will be changes in the speed and the wavelength, but not the frequency. Okay, so can I say that, let's make F the subject of the formula. F equals to V over lambda. Okay, so can I say that V1 over lambda 1 equals to V2 over lambda 2, because the frequency is the same. Okay, so what is V1? Maybe I say is VR lah. What is V2? Maybe I say is VS. Okay, VR we know what's the value. VS I do not know. I know wavelength at before it went to a shallower. Okay, maybe I call it lambda r, then this I call it lambda s. Okay, getting a bit messy, so I come over to here. So VR is actually 12, lambda r is actually 3. Now Vs is unknown, I'm asked to find. The wavelength becomes shorter, so it's 1.5. Okay, so if you work out, Vs will be 6 meter per second, which is this, right? So as what we have predicted using SSS model, from deeper to shallower, the wavelength becomes shorter, as evident from here. The speed will also become slower. Okay, so this is how we solve this kind of question.